I hope this goes well. I hope you walk away from this and you're like, bam, this is I got this. Nothing to it. So this whole unit actually that we've been doing for 5 weeks has been called polynomial functions, but we haven't really addressed them as polynomial functions. I've just spent 5 weeks trying to get you to be really good at factoring. And like I said before, I think by and large it's paid off. So that's great news. So we won't directly address just factoring anymore. There won't be any lessons explicitly on just this is how you factor. That just becomes now a tool in our toolbox that we'll use when we need to. So that was the purpose of the month and a half or whatever that was. Today is the 28th. And now we specifically will address polynomial functions. So all these things I've asked you to factor have been function rules. You just don't address them as such. They've been the meat and potatoes part of functions. So like for my first example, and this is total rookie. This is total fluff and puff here, but like in the past, what I would have asked you to do is just to factor that polynomial down. And you would identify it, I mean, instantaneously as a fluffer puffer quadratic trinomial, and you would immediately break it down. So what we're going to do today is we're going to make the jump up a step, and we're going to acknowledge it now, not just as a mathy thing, but as the rule of a function. So starting today now, we're going to address it as this. And what this means for us is that now it's not just a thing that we just toy around with for the sake of toying around with it. We now put the use of factoring into play, or the skill of factoring into play. And so the idea for today, if I can get out of this, if we all walk out of here and everything goes well today, the idea is I want you to be able to look at a graph, a function like that, and tell me three things. Its end behavior, and I'll explain what that means because it's cryptic as all get out until it clicks. Where it crosses the x-axis, those are called zeros, and when the graph of the curve is above the x-axis and when it's below the x-axis. So those are our three objectives for the day. So let me mark those, and then we'll just kind of tick them off as we go, or check them off. So objective number one is awkward, and we need to talk about end behavior. Okay, objective number two is finding zeros. And I'm going to put a little parenthetical comment right below zeros. Zeros you can also think of, we don't call them this because it's just weird, but zeros are really just x-intercepts. You can't really call them that because some zeros are imaginary and it's like, whatever. So anyways, we call them zeros. And then the third objective for the day is to find positive and negative intervals, we say. So let me just make, since I realize probably everything that's on the board other than number two is probably like, what are you talking about? So let me just make a really crude sketch really quick. It doesn't relate to the function, the problem that I have on the board. And you may not want to write this down, but if you find that it's beneficial, then get down with your bad self. So we're going to be graphing things. And actually, that's kind of a lie. We're not really going to be graphing things. We're just going to be thinking about what the graphs of things would look like. So let's say that I wound up graphing a function and it went, oh my God, take that back there, sucker. There we go. And let's say it went like this. So this is what our functions, some of them are going to start looking like. And we're used to lines. Like from Algebra 1, everything was a line, right? Linear this, linear that. I think the deepest we ever went was parabolas, little quadratic things. So if you get a curve that looks like this, here we go. So these are the three things that we study, and I'll color code this for you. So for number one, for end behavior, what we're studying is how the graph behaves as it heads on infinitely to the left and to the right. That's called the end behavior of a function, and it's significantly important. Like, you need to know how it works. And there are simple rules for it if you're just willing to memorize them, okay? So we're going to study that. That's called end behavior. The second thing, number two, I'll code him as a yellow, is the zeros. And that's something that is our mission for the day, is to study this yellow point, this yellow point, and this yellow point. I'm going to pause that really quickly. Hold on a second. And objective number 3 is to study positive and negative intervals. And so I'm going to color code that one for you purple. And so an interval is defined to be a section between two things. Like you probably already knew that, but like between 2 points is called an interval. So you'll notice that this purple interval over here, you would agree, is negative. And what I mean by that is all of the y values of the graph are negative. They exist below the x-axis, right? So any y's on that little purple stretch that I just arrowed are all negative. And then we have another interval that exists right here, and I'm just kind of, again, sketching it purple for you. That we would say is a positive interval because all of the graph's values are above the x. So obviously, duh, all the y's have to be positive. Our next little interval would exist right here, and that is a negative interval. So that's a negative interval. And then, of course, we have this infinitely long positive interval as well. So kind of putting all those things together, what we're trying to do today is create a picture of a graph based on its end behavior, the places where it crosses the x-axis, and then we determine the positivity or the negativity of the intervals based on that. Does that make any sense at all? That's the mission? Okay. So keep those 3 objectives. If you find that I get sidetracked, because, you know, I've done that before, try to keep me lined and focused on those 3 things: end behavior, zeros, and intervals. That's the mission. So to start with, I'm going to erase a bunch. I hope you got all this down. Everybody good? If you didn't, you can go watch it later and get it back. So I'm going to focus now on the problem that's on the board. And I started you with the easiest problem I could possibly think of. So to find zeros, we're going to factor, right? Of course. And so what I want to do is I want to take the meat and potatoes part of the function. We call that the function rule, the important side. And I'm going to factor it down. And so like, man, this ain't my first rodeo. So how would I factor down x squared minus 3x minus 10? It's a quadratic trinomial, so I would just break it down like this. You literally just took a quiz over this 24 hours ago. And then I would put x's here, and what else would I put in? -5 and a +2. Good. So that becomes critical to our success, that we can take a polynomial and break it into its components so that the components reveal something important for us. So if I went back, I shouldn't have erased all of that, but I'm not going to bring it back now. If you think about, you could get really lost on this part if you're not careful. So you just be careful. If you think about a graph that goes and crosses through, let me sketch another curve kind of like the last one. So just same idea. If you think about a curve that behaves like this, can you tell me one thing about that yellow point other than sarcastic answers like it's yellow? I mean, don't say dumb stuff. Can you think of one thing about it that has to be true? Yeah, Bryce? Its x value looks negative, right? But that's actually neither here nor there. Can you tell me something else about it? I agree, and that's significant, but that's not quite what I'm looking for. Yes, it's on the x-axis, but what does that mean specifically? That's what it means. I'm going to say that again just because I want to. The y value is 0, and that's really what this tons of upper level mathematics boils down to, that one fact. I'm really interested in the points where y equals 0. Mathematicians spend entire careers studying curves and when their y values are 0. Those are very significant points. So we can say the same thing about this yellow point, this yellow point, and this yellow point. I can't say that they're negative or positive, or because that's talking about their x's, which is going to be different. The one thing I can say about them all is that each of these points, the y value is 0. That is irrefutable. Do we agree? Okay. So having said that, then where we then spawn off into this lesson now is we say to ourselves, okay, so what I need is for the function's value to be 0. And by the way, I haven't said this out loud yet. When I say f of x, that's exactly the same thing to you as saying y. Okay? We use function notation more in upper level mathematics. It gives us a little bit more flexibility, but really it's the same idea as it's always been, that the y and the x are just playing off of each other, right? So what I really want to find those yellow dots is where y equals 0. And so really what that means is take a look over here at this green box. I want that box to equal 0. So where I'm at now is my function can be written like this. X minus 5 times x plus 2 equals 0. And what you're about to now experience for the next minute, you're going to be like, wait, I kind of remember this because we do touch on this in Algebra 1 when we solve basic quadratic equations. What can be true? What has to be true if this red thing and this purple thing multiply to make 0? What has to be true? X does not have to be 0. If I multiply a purple thing and a red thing together and I get 0, what has to be true about the purple thing and the red thing? One of them has to be 0. X does not have to be 0. Here's what has to be true. This thing in the red box, this thing in the red box might equal 0. Do we agree? And if it equals 0, then what would X have to be? X would have to be 5, right? And if the purple box might be the culprit that equals 0, remember the box overall is what equals 0. The factor itself equals 0. Then X would have to be -2, right? So what we just found are called zeros. Those are going to, and I'll show you this in a second, those are going to be the places guaranteed where that curve will slice through the x-axis. It will hit the x-axis at 5. It will hit the x-axis at -2. So let me head over to Desmos real quick, and let's just graph it to verify that. And you're always welcome, by the way, to play along. If you want to have your Desmos up and running, you're always welcome. But you can also just let me do it. It doesn't matter. So I'm going to head over to Desmos. And the function that we're graphing is x squared minus 3x minus 10. And I can zoom out on this so you can kind of get a better picture of the curve. But sure enough, with our own eyes, we can see 2 points of great significance. We can see this one right here. That's hard to see, I know, but it's clearly crossing through the x-axis right as advertised at -2. And then the other one, as advertised, is crossing through at +5. So by using factoring, we were able to break a polynomial down into its component pieces, each of whom reveals a place where the graph crosses the x-axis, right? That's really the primary reason why we learn how to factor, is because factoring exposes the pieces that then expose the zeros, right? So there are 2 questions left unsolved or unanswered then as it pertains to this problem. We just checked box 2, right? You totally now understand, okay, to find the zeros of a function, I factor it down and then set the factors equal to 0, and I've got all my crossing points. Easy peasy. So now the question becomes, how would I determine what this graph looks like overall? And this is the hardest part of this lesson. So if you need a 30-second break or whatever, take a deep breath, do some jumping jacks. You'll hate this part. But once it clicks, you'll go, that's easy. So what we need to study now is how this graph behaves. And I want you to notice that the graphs on the left side, what is the graph doing? As we go infinitely to the left, what is the graph doing? Say it again. It's going up. So we say then that this graph's end behavior is that as x approaches -infinity, the graph approaches positive infinity. Got it? What about as x goes forever to the right? As x goes to positive infinity, where does y go? To positive infinity also. Now I want to show you something. I'm gonna bring in another graph. You ready for this one? I'm gonna bring in x to the 4th. And I'm just gonna make up a bunch of garbage. -3 x to the 3rd plus 2x squared minus 8. And I'm gonna zoom in on that graph, that green graph. Don't worry about the interesting part of it. Don't worry about that. Worry about the ends. Trust me. So as x goes forever to the left, where does the graph go? I'll be darned. And as x goes forever to the right, where does the graph go? Let me graph another one for you. Let's do x to the 10th minus 3x squared plus 4. You see that purple graph in there? What do you notice about his end behaviors? It does the same thing. It does probably a whole bunch of other really cool crap in the middle, but that's not my concern right this second. My concern is I need you to know by looking at a graph how to determine what his arms do, because what his arms do is going to determine his landing approach as he comes into the x-axis. Could anyone right now make a theory about connecting how to look at a graph, or excuse me, how to look at a polynomial function and how to make a conjecture about what its arms do? Sutter? What's negative? Nope. I haven't gotten to that yet. I notice in all of these, and I know that I've got something in the way so you can't flip and see it. But look at, do you notice that in front of all of those, there's a positive one, positive one, positive one? Are you ready for this? How about this one? Watch this. Negative 2 x to the 6th minus 3x to the 3rd plus 8. I just don't care. Look at the black graph. Wait a second. Stop the press. This time, as I go forever to the left, where does the graph go? Ooh. As I go forever to the right, where does the graph go? So that can help kind of with what Sutter was saying about the whole negative number in the front thing. But generally speaking, tell me one thing that's true about all 4 functions that I just graphed on Desmos. Look carefully at the functions. Don't sleep through this. Be a part of this. Look carefully at the 4 functions that I typed into the boxes. They all have exponents. Do better. Look closer. Look harder. What's true? Don't even worry about the 3s. Here, I'll change those for you. I'll change this to a 5. I'll change this one to a 9. And I'll change this one to a flippin' 11 because I just don't. It has nothing to do with anything after the beginning. Look closely at the beginning. What do you notice about them all? Say it again. That it? You did it. You cracked the code. There it is. And this needs to somehow get into your notes. I don't have I used to teach this very formally as X approach. Kids were like, oh my God, what does this mean? This is what I need you to know for functional usability purposes. Christian just hit the nail on the head. Do you see how every one of those functions has an even leading exponent? I don't give a crap about the rest. Listen, I don't care about the rest. I care about that first exponent. And if the highest exponent at the beginning is even, we can generally say that the arms on the left and the right will behave the same way. Either both arms are going to go up. And yeah, there's a bunch of cool crap happening in the middle, but either both arms are going to go up or both arms are going to go down. Do you understand that? Yes. So if I'm looking at a function and it says like blah, 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 negative 3x to the 4th, I immediately go, your arms are going to behave the same. And how will I determine if the arms both go up or both go down? Swaggy B? Yes, if the number in front is positive or negative. And you can see on that 4th one that you can't see because this stupid thing keeps blocking it. You can see that on that 4th one down there, I started the function with a negative, and that's what forced both arms to shoot to the south. Got it? That is called end behavior. And again, I'm not gonna force you to write it the way we used to write it. Here's the way we used to write it, and I just learned my lesson. Like, this isn't doing kids any good. We're supposed to teach it like this, but you don't. It's okay. We're supposed to say this: as x approaches negative infinity, comma, f of x approaches positive infinity. And what I learned over the years is like that is doing no one any good. What I need you to understand about it is how to use it and put it to practice. And the practice says this: if your highest exponent at the beginning is even, the arms are going to do the same thing. And then to look a little deeper into it and see what that same thing is it up, up, or down, down, you look at the leading coefficient, the number in the front. So positive leading coefficient, even exponent, your arms both go up. Negative leading coefficient, even exponent, your arms both go down. Got it? Okay, let's talk about the next. Logically, if you're still listening at this point, your question is, well, what happens if the exponent is odd? Well, let's let Desmos kind of guide us through that. So And again, don't worry about writing down all that stuff about x, negative infinity, positive infinity. It's honestly, there will come a time where you might be interested in writing that down, but don't do it today. It's just going to mess, it's going to mook up your brain. Got it? All right, so I'm going to graph x to the third minus 4x squared plus 2. So again, there's exciting stuff, and we will talk about the exciting stuff. But all I'm interested for this 5 minutes of the lesson is how is the graph behaving as we go forever to the left and forever to the right. As we go forever to the left, what does the arm do? It goes down. And as we go forever to the right, what does the arm do? It goes up. I could do it again, and you know exactly where I'm headed with this. So I could put in like 3x to the fifth minus 4x squared plus 11x minus 3. And I'm not interested. That's a very terrible graph, by the way. I wish I'd come up with something better than that. I think it's boring. Anyways, the big awkward blue graph, as I go forever to the left, where does Army go? Down. And as I go forever to the right, where does Army go? Up. What could you say right now then is true? Generally speaking, Christian cracked the code for us last time. What can we now say is true about odd exponents? Gabriel? Right. So if the power is 1, 3, 5, 7, 9, if it's any odd number, your arms will not do the same thing. One will go down and one will go up. So we can say that by default, what we're looking at here is a positive leading coefficient and an odd exponent. Left arm goes down, right arm goes up. All right, big brainers, how can I flip it so that left arm goes up and right arm goes down? Swaggy B? Stick a negative. And you guessed it. Like, watch this. Watch the red graph right now. I'm going to zoom in a little bit. And all I'm going to do is put a negative. You ready? And it flipped. The end behavior is still opposite, except this time lefty arm goes up and righty arm goes down. There are 4 types of end behavior, and you just learned them all. So positive, even, up, up, negative, even, down, down. Let's write that down. Why don't we write this part down? And let's write it in plain dumb English, not all that fancy arrow infinity stuff. Got it? Let's do that. Let's use plain English. So yeah, none of that stuff. We don't want that today. So if we have, so all we're going to talk about is the first term, assuming that you've got your polynomial in standard form, which it should be. So that leading term is going to be all we need to look at. So if we have a positive and my x is to an even power, then we can say the arms go up on the left and up on the right. Is this workable English for you? Does this make sense? Can you picture what I mean by this? So like an example for your notes would be like if I had like 4x to the 8th. That's a positive leading coefficient and an even leading exponent. So his arms would go up and up. Yeah, and a whole bunch of stuff would happen in the middle. Let's switch it now. I'll switch colors here. Let's switch to a negative leading coefficient, but x is still to an even power. What can we say about those arms? It's going to go down, down. This will all come together in approximately 5 minutes. I promise. If it hasn't already, it will. You'll be able, when I'm done with you here in 5 minutes or 7 minutes, to be able to look at a function now and know exactly how it behaves. To the left, to the right, where does it cross, and where is it above and below? Promise. Well, I can't make that promise. I'm going to try hard, though. All right, let's switch it. An example of that would be something like negative 3x squared, right? The negative in the front and then the even on the power. All right, let's switch it to a positive, and my x is to an odd power. What can we say about those arms? This was the default one that I started with back over on Desmos. Do you remember? Say it again. Left one goes down. Right one goes up. That's going to be your standard odd. We call those odd. Your odd powered functions are going to standard go down on your left and up on your right. Okay. Start low and high. And then an example of that would be like 4x to the third, right? Positive in the front, odd on the exponent. And then our last, literally like the last possibility would be negative in the front and x to an odd power. What happens then? Up, down, right? So now on the left, my graph comes in from the left from on high and it exits on low. So it's up on the left and down on the right. And an example of that would be something like negative 3/4 x to the fifth. Who cares if it's fraction? Like at the end of the day, that's not what we're talking about. We know what the arms are going to do. And now you say to yourself, well, why do I really care? Well, think about why you have to care. Let's say that I had a graph like this, and Christian walks up to me and he says, all right, we're going to play a mystery game. And all I'm going to tell you is that the graph crosses the x-axis here, here, and here. Sketch the graph. I don't have enough information, do I? But if I can look at the function and I can see some stuff about it. So let's just say that the first term of the function, let's say he gave me, and I'm only going to write the first term because this won't even be close to accurate if I don't. But let's say that the first term that I look at that Christian gives me is negative 3/4 x to the third. And then there's going to be a whole bunch of stuff after that. But that's all I need to look at is his first term, right? And that, by the way, I don't think that's accurate. This would need to be to the fourth. I apologize. Go ahead and fix that for me real quick. If you've wrote it down, fix it. So here's what I now know. Because of what I just learned about end behavior, what are the arms of this function going to do? Oh, change it back to a 3. I'm so sorry. I hope you. How does that work? It doesn't. Just bear with me. I've been fine up until this point, and then I think I just got abducted by aliens. I apologize. So if I look at Christian's first term, if he just says, okay, all I'm going to tell you is I got those 3 dots where it crosses, and I'm going to let you sneak a peek at the very first term of my function. Do I now have enough information to make a sketch? I do. Because I look back at my notes now and I say, okay, here's what I see. I see that this number is negative, and I see that this exponent is odd. And so it's in one of my 4 categories, right? So what is the end behavior of a function that starts with a negative and an odd? That's right. It starts high, it comes in high, and it ends low, right? So if Christian said to me, okay, let's see how you can do, I know that the graph is going to come in for its approach landing from the high side, right? Because that's what it's going to do if it has that odd power. And then it's going to dip below like this. And I'm just piecing this together based on what is fact. And then the graph is going to dive back over and down, and then it's going to do exactly what the end behavior tells me it has to do. Do you see the connection there as to why without the end behavior, you'd never know how to make the sketch of the graph? If I know how the graph behaves coming in and on its exit, I can make this sketch. And it may not be entirely accurate. We're not going for that right now. We're just going for, now let's put all the pieces together. Do you see these intervals? You would agree that this interval right here that I'm writing red on is a positive interval, isn't it? And you would agree that this interval that I'm kind of squiggling in yellow is a negative interval. You would agree that this green interval is another positive interval. And you would agree that this purple interval is a negative, right? Good so far? Okay. All right. We're perched right on the precipice now. So let's revisit that last problem. That was this guy. So if you could just go back up in your notes, let's revisit him. And this will officially now come together. I don't think we get through everything today, but I'm going to try. I got 8 minutes and I'm not sure that that's realistic. So hang with me here. So let's get back to this guy, the one that we did together. Remember how we factored it and we found all the cute little zeros and stuff? So what I'm going to do now is I'm going to make my x-axis and my y-axis. And where does this graph right here I'll put a little star next to it. Where does this graph cross the x-axis? At 5 and at -2, right? So I'm just sketching those, but that's proportionally decent, I suppose. Clear? Now, if I said to Tyson, make me a graph, he doesn't have enough information if all I give him are the green dots. But if he understands end behavior, then he does have enough information. This function, you would agree, based on what I'm about to put in a red box. That red box is really important. You would agree that it has a positive leading number and an even exponent, doesn't it? So which of the 4 categories is he? He's an up-up. So if I know that it only crosses twice and it's an up-up, then I know that the graph comes in for its landing from this side like this, and it comes in for, or goes out its exit like this. You agree? Yeah. And then you can fill in the dots and make the rest of the sketch just like this. I knew I'd kind of missed that, but that's the idea. Decent sketch. Now let's talk about intervals and let's make this official, and we'll try to get through one more example. I had 7 examples. What a moron to think that we'd get through 7. So ready? Let's piece it together. We have 3 intervals on this function. One of them I'm going to make purple. There's great potential you're going to get super lost in the next 2 minutes. Watch out. So we'll call that one Mr. Purple. We'll just leave this one in the middle alone. This one is red. Got it? And then our next interval we'll call Mr. Green, and he's over here. So by intervals, what I'm talking about is I'm differentiating right now between the places where the graph is happily existing up high and the places where it's happily existing down low. How would you guys describe the purple interval? This will be the hardest question I ask you all day. It's positive, but could you describe it for me horizontally? Intervals are defined as from here to here. So intervals are defined as left to right intervals. What about this one? I'm going to write this down and you're going to make some sort of gesture, not obscene, please, as to whether or not this is even remotely sensible. We can say that there is a positive interval, watch out, when x is less than -2. That's called an interval. So let's think about it for a second. Pretend you're on the x-axis. Got it? And you go bebopping over to -2, and you start walking to the left. Where will the graph always be relative to you? If I'm right here, I'm going to make a purple dot, and I start moving. I don't know if I can grab that dot. Can I move this dot? Oh, come on, move dot. Oh, look at that. I can move the little dot. That's dope. So here I am when x equals 2, right? A -2. So if I move to the left, where is the graph relative to me? I'm always above. Will it ever not be above? That's why we just defined a positive interval. We can say that if you're on the x-axis and you're to the left of -2, the graph is above you, hence the graph is positive. Let's define another interval. I'm going to grab my purple dot again, if I can, because that was really fun. And this time, my next interval is defined from here to here. And what could you say is true about the graph at any point where my purple dot is bebopping around? Go ahead. I think you said positive, and I just can't for the life of me think that you meant to say positive. Did you mean to say negative? Yeah. Would you agree that anywhere where my purple dot is bebopping around back and forth, playing pong to the left and the right, that the graph is below me? So we need to define a second interval now. We need to say now that the graph is negative, the function's value is negative when x is between -2 and +5. If I'm in that interval, the graph is below me. It's irrefutable. And I have one more interval to grab. I'm going to grab that purple dot again if it'll let me. Good. Now here I am where there's equilibrium, right? The graph isn't above me. It's not below me. I'm on at 0. What happens is I bebop to the right. The graph is above me. So to define my final interval, I would have to say now that the graph is positive when what? When x is more than 5. So that's our last and most difficult objective of the day, is to be able to now look at the graph and define its intervals. Yeah. Yeah. Why did I put less than 5? I thank you. It's like I've never done this before. How do you feel? Scale of 1 to 10. 1, I have no idea what you just said. 10 is like I could do this in my sleep. 5? Are you raising your hand? 5? It's 8? That's dope. I want to start one more problem. Listen, there's no way we get boy, talk about biting off more than you could chew. So you think I'd never done this job before. We're going to do one more problem. You are not going to backpack bandit me. You are not going to pack up. You're not going to do that. You're going to give me a couple more minutes of your life, maybe even just one. And we're just going to get an example started so that come Monday when we reconvene, we'll be like, yeah, this is where we were. So one more. Write down this function, please. Let's get cracking, but I promise I'll get you packed up. I cross my heart. I gotta watch my watch. If I said to you, factor this thing, this is where the last quiz really comes back to help us. What would you say about it? Pull out a GCF. Good for you, Bryce. And that leaves behind x squared plus single x minus 12. And then, of course, you would factor down the white thing, and you would have x times what? X plus x minus x plus 4, x minus 3. And we would now have the conversation about what does this mean about the graph? Stop right there. We've obviously got a lot left to talk about on Monday. I'm okay with that. So good place to stop. Feel okay? All right. The only ones of you who should say I've got homework are those of you guys that did not do well on that quiz. Congratulations. You've got extra work.